Hey everyone, I'm Sajan and today I'll be sharing my work on designing, testing and comparing difference controllers for an inverted pendulum. Let's get started. So balancing a broomstick on your palm is tricky, right? It keeps falling no matter how hard you try. That's exactly how an inverted pendulum behaves. It's a naturally unstable system and needs constant correction to stay upright position. The challenge is keeping the pendulum balanced with the right control methods. In this project, I am using PID, LQR and fuzzy logic controllers to see which one works best. So this is the inverted pendulum setup consisting of a card, a pendulum and a sensor. Let's see how it works. The cards moves left and right to balance the pendulum. It's driven by DC motors, which generate necessary force to stabilize the system. The pendulum angular displacement is constantly measured by using a potentiometer, which provides real-time feedback to the controller. Based on this data, the controller adjusts the card motion to keep the pendulum upright. Since the pendulum is naturally unstable, it requires constant correction to maintain balance. This is why selecting the right controller strategy is crucial. So I am testing three controllers uh, which work best. The first one is PID, simple but effective, adjusts moments based on the past, present and future errors. LQR. LQR calculates the best way to move the card and keep the pendulum balanced using the mathematical equation. Fuzzy logic. Fuzzy logic works more like human decision making to handle uncertainty. Each control has its own strength, so I am comparing them side by side to determine which perform best. The problem is that the most students don't get hands-on experience with these controllers. Theory is great, but without real experiments, it's hard to fully understand how they work. So this project creates a learning tool where students can try different controllers and see the results for themselves. So it's just it's not just for classrooms. Inverted pendulums are everywhere. Segways and self-balancing robots use the same principle. Rockets need similar stabilization for the when the rockets launching. By studying this system, we are learning fundamentals of real-world engineering problem. So existing research. Other researchers have explored these controllers before, but usually one at a time. PID is simple but struggles with complex movements. LQI is great for precise controls, need exact models. Fuzzy logic handles uncertainty well, uh, but tricky to fine tune. So the my project is compares all the three controllers in one system, thus making it easier to see which one performs best. So what makes my project different? So it's compare multiple controllers directly in one setup. It bridges the gap between simulation and real world testing. It creates a hands-on tool for students to learn experiment. So, can this project actually work? Absolutely. I have all hardware and software needed, and I have already started running MATLAB simulations. The math behind the system ensure that we can predict the behavior and design effective controllers. To control the pendulum, we first need to understand its motion. So using Newton's law, we create equations that describes how the system behaves. This help us design the controllers that can keep it balanced. Without maths, we just been guessing. For this system, for this system work effectively, I set few design requirements. Uh, these are the requirements for the pendulum system. So to simplify the mathematical model, I also made some assumptions. So these are the assumptions, and the first I consider the force acting on the system and create the force balance equation. Finally, I convert these into a state space model, which is essential for the controllers. So we are focusing mainly on the x and theta, which is x is card displacement and theta the angle of the rotations. So now that the math is almost done, so next step is testing and refining it using the MATLAB simulations. Before touching any real hardware, I ran simulation in MATLAB to test my controllers. First, I create a transfer function of the system. So then I obtained the state space model. So building accurate mathematical took some difficulty. So uh, even small mistakes could lead inaccurate simulation. So this is my tentative timeline for my project. So this project creates Unicube because it directly compares three major controllers. It bridges simulation and real world testing. It creates interactive tool that students can use. It's not just a research, it's something practical and useful. So so far I have derived the mathematical model, simulate the system, prepare the foundation for the control design. So next step is design the three controllers and moving on to real world testing hardware. So here are the key research papers that guided my work. They cover different controller methods and applications of inverted pendulum. So thank you for your time. I hope this presentation gave you a clear understanding of my